Okay, you've been warned.
Okay. Number 13.
Number 13.
So, let's see.
Okay, so this one is on page 303. And just so that people can see the question and maybe pause the recording if they want to take the time to read it, I'll flip it up on the screen here momentarily. So 13 is the most prominent line in the spectrum of mercury, is at 253.652 nanometers, which we know is ultraviolet light because it's not quite 400. The other lines are at 365, 404, 435, and 1013. The 1013 would be infrared light. So we have the questions A, which line represents the most energetic? And we know that energy and wavelength are inversely proportional. So if we want the most energetic, we want the shortest wavelength. So that's actually going to be the most prominent line, the 253. What is the frequency of the most prominent line? So for that one, we're probably going to use the C equals lambda nu.
Yeah.
And for the energy of one photon, since we already have nu, I'm going to use E equals lambda nu instead of E equals hc over lambda, because when I use E equals h nu, I only have to put two things into my equation. Whereas when I use hc over lambda, I have to use three things. Does that make any sense? And I'll be showing you these in just a moment. And are any of these lines found around in the spectrum of mercury shown in figure 6.6? And for that one, they only show visible lines for mercury. So I'm looking at two visible lines that we would see in mercury. And if we learn the spectrum from low wavelength to high wavelength or long wavelength, it's vid-Gyur. So 400 would be violet and 435 would probably also be violet or indigo. So those would be the colors, but let's do the calculations. Is that kind of what you want to see?
Yeah, I did fine I got the velocity, but converting the second half of B, I got confused. And I think it's a simple confusion.
Okay.
So I just wanted to see how you worked it out.
When you say velocity, do you mean frequency?
Yeah.
Okay, thank you. We just want to make sure because the symbols do look a lot alike.
Okay.
So this is number 13. And we're going to be using that the wavelength is 253.652 nanometers. And we've already said that A, the most energetic, is the 253.652. And what are the phrases we would use to justify this? And the answer would be this. So you'd write that out. You'd say wavelength is inversely proportional to the energy. So this means large energy translates into short wavelength. So those would kind of be the phrases you would use to explain it. And here we want the frequency of the most prominent line. So I'm going to use C equals lambda nu, which means that nu is equal to C over lambda. And so I'm going to write in 2.998 times 10 to the 8th meters per second for C, and lambda 253.652 times 10 to the minus 9 meters. I'm not going to monkey around with the nano. I'm just going to substitute 10 to the minus 9 for nano right away, because that's what nano really means. Okay, and when I estimate this answer, I know that 2.9 over 253 is like 1/100th, or close to that value. And this 10 to the minus 9, when it goes in the numerator, becomes 10 to the positive 9. So I get 10 to the 17. So 1/100 times 10 to the 17th is roughly 1 times 10 to the 15. So that's my estimate. It's going to be bigger than 1. 2.998 second EE8 divided by 253.652 second EE -9. And I get 1.182 times 10 to the 15. And the units here are going to be per second is what we would say.
Okay.
So that's the frequency. Now, B also asks us, what is the energy of a photon with this wavelength? So I'm going to use not this one. I'm going to use this one. And the reason I'm going to use this one is because I only have 2 things to put into the equation. So that's one less thing for me to screw up. In Tony's world, the more you have to do, the more likely it is to make a mistake. So here we can see that the seconds cancel and we're going to be left with joules. And here, if I estimate the answer is going to end up being something like 8 maybe times 10 to the -19.
You could still use the other equation, right? You would just have to use the wavelength instead.
That's right. But
Okay.
again, I wouldn't use it because I only use 2 things here.
Right.
So 7.831, so close to 8 times 10 to the -19 joules. And just to show you that we get the same answer both ways, let's do the 6.626 times 10 to the -34 joule seconds for H, 2.998 times 10 to the 8th meters per second. All of this divided by 253.652 times 10 to the -9 meters. And I'm going to plug this into my calculator. Funny thing is, I could just be typing nothing in my calculator and just say, oh, look, and it comes out the same. But here you can see I've got the 6.626 times 10 to the -34. And there's my speed of light. Oh, I made a mistake though. You see that? 9.8. And then divided by 253.652 second EE -9. And we still get that 7.831 times 10 to the -19. Okay, so yeah, so we can do it either way. But you know, when I look at all of this, oops, and I don't want that there. When I look at all of this, I think that this is easier than this. Okay, so for an answer like that, I would expect to see things like this, this, this. And for C, are any of these lines found in the visible spectrum? C, you'd say the 404.656 nanometer, and that's going to be violet. And the 435.833 nanometers, that's going to be probably violet or indigo. Now, I don't know how they draw them in your book, but the reason I come up with these colors is that we know that when we go 400 nanometers to 700 nanometers, it's Vib Gyor. And you might wonder, how is Tony able to write Vib Gyor underneath those numbers so wonderfully so that all of the letters are nice and evenly spread? And it's because I have a master's in chemistry. Okay. Actually, that's not it. I just try to put the G in the middle because the G's in the middle. And that's how I space things. Okay, so you can see that if this is 400 and we space these out, this would be 500, this would be 600, this would be 700. So if that's 500, 435 is right around in here. So that puts it like in the violet indigo region as far as I'm concerned. Any questions there?
No.
No, so we can just approximate, right?
Yeah, you are not going to be asked what color is it. You might be asked what color might it be, but I'm not expecting you to say, yeah, it's going to be blue-green because it's right between blue and green. The numbers that I know are that 400 is violet, of course, 700 and actually almost 600 to 700 is red, and green is 500. Those are the ones that I kind of know, the ends in the middle. And the interesting thing is that green is in the middle as far as these letters are concerned, but green is more like 500, which is closer to the 400 region. So it's really more like this. Vib, whoops, forgot the yellow. Where red really goes almost from 600 to 700. Okay. Okay, let's put that away. Other questions you'd like to ask?
Yeah. Number 23, we did together, I think, yesterday. But
Okay.
I don't remember how we got the mass of the electron, I guess. I'm wondering if that's just a value we need to know,
No,
or
that's the value you'd be given. And I want to remind you that you actually got the mass of the electron by looking at 24.
oh yeah. Okay. So that will
So
be given.
that's not a mass I expect you to remember. In fact, I expect you to remember that the mass of an electron is 0 AMU.
Yeah.
And what is the mass of a proton? 1.00 AMU. And the mass of a neutron is 1.00 AMU. I expect you to know those numbers because they're so easy to remember, 1 and 0. The mass of an electron, you know, if this were a physics class, I'd probably want you to know that, but it's a chemistry class and we don't really use that mass too often. So I don't really expect you to know it. I'd rather have you memorize Planck's constant than the mass of an electron because you're using Planck's constant all the time.
Yeah.
But I don't have you memorize that. But then again, you get your little index card.
Okay.
Okay. So does that kind of answer the question for 23? Where do we get the mass from and are we required to know it?
Yeah.
Okay, excellent. Other questions? Okay, if you guys don't have any questions, then let's just call it quits because it's Friday. Okay, I'm kidding.
No.
We'll do some problems here. I think so we did number 32. We left off on that one last night. Does that sound about right? How many subshells occur? Or maybe we didn't do that, but let's go ahead and just continue doing some problems here. And I'm going to give you a little bit of background with each problem to help you understand how I arrive at the answer. Okay, so how many subshells occur in the electron shell with the principal quantum number n equal 5? We're going to answer this from 2 points of view. One point of view is technically. And the answer to technically is that the number of subshells is 5. So how do I know that? And the answer is that the number of subshells in a shell equals the shell number. So if n is equal to 1, L can be equal to 0. That's one subshell. If n is equal to 2, L can be 0 or 1. Do you remember how we count starting at 0 for L's? So this 0 is like the 0th subshell. This 1 is the 1th subshell, if you will. So here you can see that when we put the number of L's down, it's always going to equal the subshell or the shell number. So technically, for the 5th shell, there's 5 subshells. Now, really, there's 4 subshells. And it's going to be 5, 0, 1, 2, 3. I would not really expect you to be able to answer this from the really point of view, but definitely from the technical. So from the technical point of view, the number of subshells is the shell number. Any questions there?
Nope.
Okay. Okay, which of the following represent valid sets of quantum numbers? For those that are invalid, briefly explain. So I think we did a little bit of this, you and I, Charlotte, but we're going to do this again. So A is invalid. And we could explain this being invalid from 2 points of view. One is that if n is equal to 3, L can be equal to 0, 1, or 2, but not 3. So this is invalid because L is equal to 3. Or you could say this, if L is equal to 3, N must be 4, 5, 6, or 7. It can't be 3. So you cannot have L and N be equal. N has to be bigger than L. Okay, B is valid. C is valid. D is invalid. And we could answer this from 2 points of view. We could say that for L equal 3, M sub L can be -3, -2, -1, 0, +1, +2, or +3, but not -4. So the range of M sub L goes from +L to -L. And you can't see what I'm writing. So let me move my sheet of paper up. So M sub L can be -3 all the way to +3, but not -4. So that's one way it is invalid. But you could look at it from the point of view of M sub L being a -4. For M sub L to be equal to -4, L must be 4 or greater, which means that N must be 5 or greater. So from the point of view of having a -4, we would want that L to be, we would want that L to be a 4. That would work. But then we want N also to be 5 because you can't have a 4 and a 4 for M sub L or for L and N. Okay? So I think that when we answer from both points of view that, maybe the number to the right is correct and the numbers to the left are wrong, it gives you a better idea of, or more practice in dealing with these quantum values, okay? Okay, so when we look at these values, if we look at B, 210, these represent an orbital, and they also represent a standing wave. And what was that symbol we used for a standing wave?
Psi.
Psi. So if you play Pokemon and Psyduck is one of your favorite characters, then you've heard that psi character before, right? You know what I'm talking about when I say Psyduck?
Yep.
You should be ashamed. I should be ashamed for knowing Psyduck.
I am not ashamed.
I know. That's not something to be ashamed of.
Oh, come on.
Pokemon?
Yeah, Pokemon is a kid's game. Come on.
Yeah, but that was our childhood. At least that's how I grew up.
Yeah, I was a kid.
Okay. Were
No.
you a kid in Japan?
No.
Because that's
Or a kid in the US.
the
Pokemon was big here when I was a kid.
Japanese thing. You know, when I was living in Japan, when I was 10, I knew that a lot of the Japanese things I was watching would be really popular in the US, but there was a cultural gap.
Mhm.
And now a lot of those cultural gaps have disappeared. I mean, what is the name? There's like a Korean boy band that is like really famous here in the US, and half the kids can't even speak English.
Is it like BTS or I don't know, something?
Yes, yes. And
Is that it?
there's the BTS Army, which I guess are the people who like to listen to them.
Wow.
So
Yeah, I knew K-pop would become a thing at some point
yeah.
when
So
I was a senior in
that's
high
not
school.
that's not your childhood. You guys are old for that.
For K-pop, yeah. I mean, no, actually, I grew up watching like K soap operas when I was in high school, but on the like Korean channel.
And those soap operas are they're like limited run, right? They're like 10
Yeah.
episodes and they're done, right?
That was before Netflix and all that. But now with like Netflix and like everything streaming, I'm sure people have access to all kinds of.
Yeah, Korean and Japanese TV have both had those limited run soap operas that are like 10 episodes long and they're done.
Yeah, exactly.
And we always enjoyed watching them in Seattle because we got a Japanese channel and we'd watch these Japanese soap operas. Okay, so let's look at number 36. What is the maximum number of orbitals that can be identified with each of the following set of quantum numbers? Well, the best way to answer this is to fill out the whole list as follows. So what can M sub L be? It can be -3, right? Or it can be -2, or -1, or 0, or +1, or +2, or +3. Now this 3 goes all the way down to here. This 4 goes all the way down to here. So you could have a 4, 3, -3, a 4, 3, -2, and so forth and so on. This is an orbital right here. And this is called a 4f orbital. Now, why is it called a 4 orbital? Because this is in shell 4. Why is it called an f orbital? It's because L is equal to 3. If you guys recall, for SPDF, where do we start numbering?
0.
0, 1, 2, 3. So F corresponds to an L equal 3. Okay, so how many orbitals do we have here? 1, 2, 3, 4, 5, 6, 7. So 7 orbitals total. And we could even say 7 hyphen 4f orbitals total. Okay, so that's A. For B, we have n equal 5. Well, we're going to answer this from the technical point of view, okay? And so for n equal 5, L could be equal to 0, 1, 2, 3, or 4. So this is from the technical point of view. L can be anything up to n minus 1. So that would be 4. M sub L, now here instead of going vertical, I'm going to go horizontal. Could be 0, -1, 0, +1, -2, -1, 0, +1, +2, -3, -2, -1, 0, +1, +2, +3, and -4, -3, -2, -1, 0, and +1, +2, +3, +4. So like we saw above, each one of these m sub l's is an orbital, right? So what do we know down here? Each one of these is an orbital. And I believe we were asked how many orbitals, right?
Yeah.
So we have to count the number of m sub l's we have. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And do you remember this one is? So we talked about this one last night.
Yeah. 1, 3, 5, 7.
And
Right.
here I am counting them individually when we could just add them up. 1 + 9 is 10, 3 + 7 is 10, +5 is 25.
I have a question. We're doing the technical
Yeah,
on an exam. You're gonna want actual, correct?
no, because you don't know which ones are actual. That's not really until chapter 7.
But chapter 7 will be covered on the next exam.
Oh yeah, then I will.
Okay. So
I'll expect both technically and practically.
okay.
Okay, so letter C for n = 2, L = 2, I'm going to go horizontal again. -2 plus -2, -1, 0, +1, +2. So 5 orbitals. And what type of orbitals are? Oh, actually, none. Whoop, none.
Oh yeah.
And why is it none?
It's not valid.
2 cannot equal 2 for N and L, right?
Okay.
The biggest L can be is 1 less than N. So C is none. You see the mistake? I went straight to L and I said, okay, well, if L is this, without looking at to see if these two would work together. So remember that when you join the Marines and you become a Marine drill sergeant, you can't just focus on one member. You have to look at how the whole group integrates. I know that's probably high on your list to become a Marine. Certainly high on my list. Okay, it's not really on my list at all. I'm way too old. Okay, so for this one, can we have a 3 and a 1?
Yeah.
Absolutely. And can we have a -1?
Yeah.
Absolutely. Now here, they're telling us m sub L is -1. They're not giving us any other options. So how many orbitals is this?
1.
1 orbital. And what kind is it? A 3.
P. Wait. P. Oh.
3p is correct. SPDF. And you know what? Writing this out again and again and again is going to help you realize that when you look at this number 1, it's going to be a P. So writing this out repeatedly is a good thing. Make it almost second nature.
Yeah, just remembering that 0.
Yeah. And, I tell you, if you write this down 10 times and then another 10 times, it'll probably be yours forever. You'll probably, be on your deathbed. The last thing you're going to think of is SPDF 0123. Oh my God, I hate Tony.
All that together.
That's what you're going to die thinking.
I hope not. I hope I have loving thoughts on my past.
Well, maybe this will be your loving thought. Oh, thank God Tony taught me that. Probably not. Okay. So are we good on 36?
Yeah.
Okay, let's go to the next one. Briefly explain why each of the following is not a possible set of quantum numbers for an electron in an atom. Now, I guess based on this, they actually teach you about the 4th quantum number. The 4th quantum number is called the spin quantum number. So let's look at quantum values again, or quantum numbers. There's N, there's L, there's M sub L, and there's what's called M sub S.
Right.
This is the principal. This is the angular momentum. This is the magnetic. And this is the spin quantum number. And the values for N can be 1, 2, 3. L is going to be 0, 1, 2, all the way up to N minus 1. Magnetic is going to be from negative L to negative 1, all the way up to positive L. And for a spin quantum number, it's either plus 1/2 or negative 1/2, one or the other. So do you remember before we were talking about a 2, 1, and M sub L maybe a 0. This is an orbital. This is a 2s, or excuse me, a 2p orbital. Okay. For this orbital, there are two sets of quantum numbers. You can have a 2, 1, 0 minus 1/2 and a 2, 1, 0 plus 1/2. This is an electron in a 2p orbital. And guess what this bottom set is?
The same thing.
It's an electron in a 2p orbital. Now, for L, we often use a letter designation, right? For these guys, we often use a letter designation also. So this is going to be minus 1/2, and this will be plus 1/2. So we call it spin up and spin down. Spin up, spin down. And the magnetic spin quantum number arises from the fact that when you have an electron and it is rotating or spinning, it actually makes a magnetic field so that you end up getting a north and a south. And if your electron is spinning in the opposite direction, you get a north and a south like that. So opposite spins have opposite poles. And an interesting thing is when you combine two electrons with opposite poles, they end up having no pole altogether. The poles cancel out. Okay, so a little bit of background there so that we can do this problem here. Explain why each of the following is not possible. So for A, N cannot equal L. Fair enough?
Mm-hmm.
For B, M sub S cannot equal 0. What does M sub S have to be?
Plus or minus 1/2.
Plus 1/2 or minus 1/2. How about C? What's wrong with C? M sub L cannot equal -2 for L equal to 1. And for these, I haven't gone backwards to explain why they're wrong. For instance, you could say that if M sub L is -2, L has to be at least 2. That would be another reasonable explanation. For B, there is no other explanation other than M sub L. M sub S cannot be 0. Okay. For A, you could do a back explanation. You could say, well, if L is going to be 2, N has to be at least 3. Okay. So I got my second shot, and I'm not feeling fluey. I'm feeling like someone punched me in the arm, and that's about it.
Yeah, yesterday you were complaining a little bit about it.
I was complaining about being tired, but I'm always tired, Issa.
Okay.
In fact, what you guys don't know is right now I'm taking a nap, but I'm talking in my sleep. Okay.
That's
State
great.
which of the following orbitals.
That would be great, right? If I could do that. Work while I'm taking a nap.
Quite honestly, when we're done here, I'm going to go lay down and take a nap. This is what old men do. Old men sleep a lot. So if you like cats, then you will like old men because they sleep a lot and so do old men.
Charlotte's like, okay.
We'll even purr if you rub our stomachs. Okay, let's see now. This doesn't look quite focused, does it? Let's see if we can make it a little better or if this is going to make it worse. You know, maybe it's just my glasses. State which of the following orbitals cannot exist according to quantum theory. So here we're looking at 3p, 4s, 2f, and 1p. Briefly explain your answers. So can a 3p exist? Well, I'm going to do this for each of these. Now, what would p be for the value of L?
1,
1. How about a 4s? What's the value for s?
0.
0. It sounds like such a chore.
I'm thinking really hard.
Okay, what about an F?
3.
Now, see, this is one of those things where if you're thinking hard, you got to make it easier for you to think easy. So how do you make it easy? I'll show you.
Just write it down.
I'm trying to do it without looking at my note card.
Well, what I'm saying is just write it down. And now you
Yeah.
don't think anymore. And you say, okay, 2F, F is 3.
That's what I do. I have to write everything down because I feel like if I try to do it in my head, then I'll make a mistake.
Exactly. You know, if you know what it is and you can write it down and you refuse to write it down, that's like the guy refusing to take directions on how to get somewhere. No, I don't want directions. I'll find it. You know, they think they know it, but if they wrote down the directions, they'd probably get there a lot faster. My dad always said, you know what, but I like to drive. I like driving. That's why I don't want you to tell me how to get there. Dad was
Just an excuse.
Dad was a character. So 1, and what is P? A 1. And this is not possible. And what kind of answer is this based on what they ask?
3.
Nope, not very good. Briefly explain your answers. I did nothing to explain. So here we could explain all of these with the idea that the largest L can be for n is n minus 1. So here, the largest L can be is n minus 1. That's a 1. The largest L can be for n minus 1, that's a 0. So here, largest L is 1, and the largest L is 0. So that's what we're looking for when they want you to briefly explain your answer. Any questions about that?
No.
Okay. Okay, write a complete set of quantum numbers for each of the following. So I'm going to let you do this, and when you're done, let me know. Just give me, I'm done. Are you guys ready?
Yeah.
Yeah.
Okay. So for A, we should all have a 5 for N. For L, I wrote my little chart down here. So I know that it's a 5F, so I've got to write a 3 there. Okay. Now for M sub L, you have a number of choices. You could do a -3, a -2, a -1, a 0, or a +1, or +2, or +3. So any of these is possible for M sub L. So if you wrote down 530, that's perfect. 5, 3, -3, that's perfect. Any of those combinations, okay?
Okay, so we can pick any of them.
You can pick any one of them.
Oh,
I
okay.
just wanted to show you all 7. But it just says a complete set, which means 5, 3, and any one of these numbers.
Okay.
So an example would be 5, 3, 0. And it's really hard to go wrong with the 0 because any subshell will have a M sub L of 0, right?
Right.
If L is equal to 0, you're going to have a 0. If L is equal to 1, you're going to have a 0. If L is equal to 2, you're going to have a 0. So 0 is a hero in this case. So for 4D, here's my D down below. I'm going to put a 2. And guess what number I'm going to put here?
0.
0. Because 0 is a hero. And we talked about this yesterday. This is Humboldt County. So there's 420. Oh, wait. Is 420 popular in Del Norte?
I wouldn't know.
Don't you have a paper up there?
A what?
A newspaper?
Oh, yeah.
If they write articles about 420, then you have to say it's popular. Okay, S is 0, right? And for this one, it has to be a 0, doesn't it?
Yeah.
You have no choice. But again, 0 is the hero. It's kind of your fallback for if you get to choose an M sub L, choose 0. Hard to go wrong with that. Okay, any questions about this one?
No.
Okay, a given orbital has a magnetic quantum number of M sub L equal -1. This could not be a F orbital. Well, here, maybe we do this. S, P, D, F, 0, 1, 2, 3. Are you with me there?
Right.
And guess what I'm going to do here? I'm going to write down all of the M sub L's that are possible. This can be a 0. This can be a -1, 0, or +1. And this can be a -2, -1, 0, +1, +2, -3, -2, -1, 0, +1, +2, +3. And technically, when I got to this point here, I could tell that, you know what, P's, D's, and F's are going to be okay. S is the only one that's not going to work. So, cannot have M sub L equal -1. Okay, they walked away. That's always the post office. They knock on the door and leave a box so that no one walks away. Someone doesn't come and steal your box.
Yeah.
But I'm right here, so I'll be able to tell. So any questions about which one of these cannot have an M sub L equal to 1? Or excuse me, -1?
No questions.
Okay. Okay. How many nodal surfaces through the nucleus, planar nodes associated with each of the following? This is something that I don't really care if you know, but the number of planar nodes for a subshell or for a orbital is equal to L minus 1. Actually, let me take that back. So here, an s orbital has no planar. A p, this is an s, this is a p orbital. A p has one planar node, and a d, which looks like a four-leaf clover, has two planar nodes. So here, if we look at the values here, 0, 1, and 2, right, SPDF, the number of planar nodes is equal to the value of the subshell. So the subshell number is equal to the planar nodes. So for this F, how many planar nodes do we have?
3.
3. How about for a 2p?
1.
1. How about a 6s?
0.
0. Now I'm thinking the next question is going to be for spherical nodes. I hate that question. Thank goodness we didn't find that. In what spectrum, in what region of the electromagnetic spectrum for hydrogen is the Lyman series of lines found and the Balmer series? Now, this question does not expect you to know what the Balmer series is or what the Lyman series is. What they expect you to do is go find it in the book. So I'm going to show it to you in the book, okay? So this is going to be on page 200 and something.
Is it 284?
It could very well be. That sounds about right. No, I'm going to call it on page 289. Because here you'll see at the top the Lyman series and the Balmer series.
Oh, yeah, yeah.
Okay, so here, if we look at the Balmer series and we look at the wavelengths, we see that they're 400 to 656 nanometers. So that is visible light, because visible light is 400 to 700, okay? Now the Lyman goes from 93 to 121 nanometers. Shorter wavelength means more energetic light. And what's just more energetic than visible? Ultraviolet. So that's how you would come to the conclusion that this is ultraviolet, not because they say so right here. They do. But if we look at it, we say, hey, shorter wavelength more means more energy. And the light that has more energy than visible, but is right next to visible, is ultraviolet. And it's the same thing here for the Ritz Passion series. What would we say for the region here? We'd say, well, the wavelength is a little bit longer than visible. Longer means it's a little bit less energy. And the light that has a little bit less energy than visible would be infrared. So these are infrared. Capiche? So that's how you would explain these if you weren't looking at the picture that already tells you. What is the maximum number of
So,
Oh, I'm sorry, go ahead.
so for the Lyman series, the question was like how, in what region? So is the region just the ultraviolet, invisible?
Ultraviolet, and the Balmer
Oh,
is
that's the region? Okay.
Yeah. So the regions are gamma, X-rays, ultraviolet, visible, infrared, microwaves, or radio waves.
Okay.
Those are the regions. Okay. What is the maximum number of s orbitals found in a given electron shell? So a given electron shell, what are they talking about here? Well, let's look at these, N, L, and M sub L. What does N tell us?
Shell.
The shell. So in a given shell. So here's a 1 L is 0, m sub L is 0. This is an s orbital, right?
Mhm.
Well, s subshell, I should say. And this is an s orbital.
Mhm.
And in fact, it's a 1s orbital. N could be equal to 2, L could be equal to 1, and m sub L could be -1, 0, or +1. Now, this is a 2p, this is a 2p, and this is a 2p. Now, if you have 2, can L be equal to 0?
Yeah.
Absolutely. M sub L is 0, so this is a 2s. So here, if you look at this, these are all of the 2 orbitals, all of the orbitals in the second shell. How many of those orbitals are a s orbital? How many of these are an s orbital?
1.
1. And here, these are all of the first shell orbitals. And how many of these are s orbitals? 1. So what you're going to find out is if we go to the next one, and I'm going to do this in reverse, instead of doing the 2's first and then the 1's and the 0's, I'm going to do the 0 first. This is a 3s. This is a 3p. This is a 3p. This is a 3p, and so forth. Here, we're going to see that we have 3p orbitals, a 3s orbital, and we're going to have 5 3d orbitals for a total of how many? 5 plus 3 plus 1, 9 orbitals in the fourth shell. How many of them, or in the third shell, I should say, how many of them are s orbitals?
1.
1. So you quickly learn that there's only one s orbital for every shell. Only one. So what's the maximum number of s orbitals given in an electron shell? 1. What's the maximum number of p's? Well, here we've got 1, 2, 3, 3 p's. 1, 2, 3. How many p's can you have? 3. How many d's? 5. And how many f's? 7. Okay. And another way to realize this answer is to understand that when you have L is equal to, I'm going to go with 5, m sub L here I'm going to go 4, 3, 2, 1, 0. M sub L can be 0, -1, 0, +1. Actually, I don't want to do it this. Forget this. I don't know what I'm trying to tell you there. See, this is what happens when I get tired. I think I have something really cool to tell you, but I really don't. Okay. Sketch a picture of the 90% boundary of an s orbital and the px orbital. Be sure the latter drawing shows why the p orbital is labeled px and not py, for example. Okay, so what we're going to do here is we're going to do something different. We're going to draw the 100% boundary for the s orbital. So the 100% boundary for an s orbital, it's called the universe. So this boundary is where you will find the electron 100% of the time. And the answer is somewhere in the universe. So every atom has a 100% boundary that is the universe. Now, the 90% boundary is going to be a lot smaller than the universe. And in fact, the 90% boundary is probably on the orders of picometers in wide. The 90% boundary is probably around 100 picometers. Okay, 100-ish. That's the 90%. Okay, so for an s orbital, it's going to look like this, where the nucleus is at the center of a sphere. And a lot of times you'll see me do one of these things. That's supposed to be the reflective surface of the sphere, so it looks like a sphere instead of just a circle. I guess if you were a real artist, maybe you could do things like this and kind of like shade it in. All right. Now for a p orbital, so this is an s orbital. For a px orbital, you'd want to do this. And there's your px. And the reason I draw the coordinates there is because they say, make sure that it looks like a px and not a py. What does a py look like? A py looks like this. And you can imagine what a PZ looks like. I'm not going to try and draw it because it just gets too messy.
So what's
Okay.
the 90% boundary?
What's that?
What's the 90% boundary?
It's also like 100-ish picometers. What you should really be asking is this. How big is a 2s orbital compared to a 2p orbital? That's what you should really be asking. And the answer is this. When you look at a 2s versus a 2p, if this is your 2s, then this is roughly your 2p. So they're about the same size. Okay?
What was the question asking again? I'm sorry.
Yeah.
Draw a picture of the 90%
Oh.
boundary surface. So what they're really asking you to do is draw a p orbital. That's all they're asking.
Okay.
I was
Okay.
just confused about like how the question connected to what you were saying.
So here, if this is a 90% boundary surface, what would a 95% boundary surface look like?
I mean, can't really draw that.
95%.
Bit bigger.
It gets bigger. What would an 80% look like?
Small.
Smaller. So they're not trying to be tricky. They're just trying to say, hey, when we draw these diagrams, they show where you're likely to find the electron 90% of the time. But they also don't give you a distance to go with that. And the distance is really the size of an atom.
So basically they just want us to know the shape of each orbital and like the orientation of it.
Yes, that's correct.
Okay.
Okay. Excited hydrogen atoms have many emission lines. One series of lines called the fun lines occurs in the infrared region. It results when an electron changes from higher levels to a level of n equal 5. Calculate the wavelength and frequency of the lowest energy series of this lines. So here, the first thing that I'm going to key in on is that it's an emission.
Mhm.
So energy is emitted.
Mhm.
Now, if this is n equal 1 and this is n equal 2, when you do that, energy is absorbed. When you do this, energy is emitted. Now, the reason I'm drawing this is so that you can see that for an emission, we have to start high and go low. Secondly, blah, 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 blah changes from a higher energy level to a level with n equal 5. So I can now adjust this drawing and put n equal 5 and n equal question mark. So I could have, 6, 7, I could do n equal 8. But if it ends up in 5, it's infrared light. And they want us to calculate the wavelength and frequency of the lowest energy line. Well, which of these lines looks shortest? That's the lowest energy.
65.
Shortest, therefore least energy. So that means that the final is n equal 5 and the initial is n equals 6, correct?
Mhm.
Okay, so how do we calculate the wavelength and frequency of this line? First, we want to calculate the energy, and that it doesn't actually tell us to calculate the energy, but we really want to calculate the energy first. So first, we're going to calculate the change in energy, then we're going to calculate the frequency, and then we're going to calculate the wavelength, okay?
So we would use the Rydberg's constant equation.
Yeah, to calculate the change in energy, this is the way I'm going to do it. Change in energy from 6 to 5 is equal to negative RHC 1 over n final squared minus 1 over n initial squared. And this is an excellent equation to have on your card.
Mhm.
And here, this is negative 2.180 times 10 to the minus 18 joules, because R times H times C is this value. And the final we can see is 5 squared, and the initial is 6 squared. Now we know that 1 over 5 squared is 1 over 25, and 1 over 6 squared is 1 over 36. So we're looking at some pretty small numbers. So whatever we get here times that should end up being even smaller than this number. So the way I would put this into my calculator is I would put down 1 divided by 25 minus 1 divided by 36. So I do the 5 squared in my head and the 6 squared in my head. And then I would take that value multiplied times 2.180 second EE negative 18. And I get 2.664 times 10 to the minus 20 joules. And that's a negative value because energy is emitted. And then I'm going to calculate the wavelength, or excuse me, the frequency. So the energy is equal to h nu, which means that the frequency is equal to the energy divided by Planck's constant, which is minus 2.664 times 10 to the minus 20 joules over 6.626 times 10 to the minus 34 joule seconds. Now I know that negative 34, when it ends up in the numerator, becomes positive 34. So basically I'm going to have like 0.5 times positive 14 or 5 times positive 13. So I get 4.021 times 10 to the 13 per second. Now for 3, we can do it one of 2 ways. We can do C is equal to lambda nu, or we can do E equals H V over C, or over lambda. I'm going to do it this way, where lambda is equal to C over nu, which is 2.998 times 10 to the 8th meters per second, all over this 4.021 times 10 to the 13 per second. And I get 7.455 times 10 to the minus 6 meters. So this is the kind of work I would expect to see for an answer like this. And then the last question that they didn't ask that we're now going to ask is this: what region of the electromagnetic spectrum? So while you guys are working on that, I'm going to pick up my package. So what region of the
So you
electromagnetic?
just got a Prime package,
Pardon me?
Amazon Prime.
Oh, well, if you look at the package,
Yeah. Ulta.
clearly it's not for me.
Is it skincare for your
Yeah.
some moisturizer?
Clearly it's not for me.
Sorry about that, Tony.
I'm just saying, if I use products like that, I'd probably look a little bit better than I do. But I worked hard for my crow's feet. I've worked hard for my liver spots. I've worked hard to look this rugged. I'm not going to try and mess that up with some sort of beauty product.
True.
Okay, so have you figured out the spectrum? This is what I would do. I'd multiply by 1 nanometer per 10 to the minus 9 nanometers, excuse me. And I would find out that this is 7,455 nanometers. And so I know that this is longer than 700 nanometers, which is visible light. So that means it must be less energetic than visible. And so that means infrared or microwaves. Now, we don't really need to do all of that because they do tell us what occurs in the infrared region. So the infrared region actually goes higher than I thought. I thought it went to like 4,000 nanometers, but it must go much higher. I don't know how high though. And if I don't know how high infrared is, do you need to know how high? No.
Okay. So we just need the calculation, right?
Yeah, the calculations, okay. But you do need to know, you need to be able to make a
visible
educated guess as to which part. So if it's visible, you should know it, period. Mm-hmm. If it's infrared, you should know it because it goes down to like 0 nanometers or 1 nanometer. And if it's infrared, or excuse me, I said that backwards. If it's ultraviolet, it goes down to about 1 nanometer, something like that. If it's infrared, clearly now we know it goes up to like 10,000 at least. So you should probably know that.
Do we have another chart for the electromagnetic spectrum other than the?
No, there are no numbers there. So that's why it's not crucial to know what numbers except for the numbers they give you, which are for visible light.
Okay, all right.
Okay, how about we do one more and then call it quits? Is that okay?
Okay.
So we'll do this number 46 or 56, I'm sorry. Radiation in the ultraviolet region of the electromagnetic spectrum is quite energetic. It is this radiation that causes dyes to fade and your skin to develop a sunburn. If you are bombarded with 1 mole of photons with a wavelength of 375 nanometers, what amount of energy in kilojoules per mole of photons are you being subjected to? Now, this one is a great question because it shows you the kind of work you have to do. So, how do we calculate energy? E equals h nu, or E is equal to hc over lambda, right? When we're talking about photons. So given that we're given the wavelength, do we want to use the top equation or the bottom equation?
Bottom one. Let's
do the bottom one. Even though it has 3 parts to it, because we're given the wavelength, we're going to use it. So we have 6.626 times 10 to the minus 34 joule seconds, 2.998 times 10 to the 8th meters per second, and 375 times 10 to the minus 9 meters. And I'm going to do a quick job of estimating. 3 or 2.998 times 6.6 is 20. 20 divided by 375 is not even 1/10, right? It's like 1/20th, which is like 0.05. Okay, -9 when I put it up top becomes +9, and 8 is +17. Positive 17 and -34 is -17. So when I combine these two together, this is like 5 times 10 to the minus 2. So I should get like 5 times 10 to the minus 19. That's my estimate. And I get 5.30 times 10 to the minus 19. And what are the units here?
Joules.
Joules. So
And you have to convert.
what's that?
You have to convert to kilojoules.
Yeah.
We should convert to kilojoules. So let's go ahead and do that. 5.30 times 10 to the minus 19 joules times 1 kilojoule per 1,000 joules. So we get 5.30 times 10 to the minus 21 kilojoules.
My calculator gave -22.
Yes, it's correct. Because I can't add 3 and 19. Okay, so this says for a mole, this is the energy for 1 photon. So this is really per 1 photon. So we know that 1 mole of photons is equal to 6.022 times 10 to the 23rd photons, right? So let's multiply times 5.30 times 10 to the minus 22 kilojoules per 1 photon and see what that turns out to be for a mole of photons. And here, can you see that 6 times 5 is 30-ish? And 23 times -22 is 1. So we're going to have 30-ish times 10. So we should get around 300. Fair enough?
Yeah.
Probably closer to 315 because, or 318 because of this guy. What did I say? 318?
Yeah. It was really close.
319. Okay, so I'd expect to see this work. I'd expect to see this work. And I'd expect to see this work for a problem like this. Now, this is really 319 kilojoules per mole, right?
Yeah.
What if you were asked to calculate the wavelength? What would you do? What you would probably want to do is something like this, right? If you wanted to calculate the wavelength, you know the energy is 319 kilojoules per mole. So you'd plug that in for energy, you have H and you have C, and you think you're home free, right? But you can't. You first have to calculate the energy per 1 photon. Then you can use this equation, because that equation is for 1 photon, not for a mole of them. So you will see a problem somewhere in your book where it says, here's the energy per mole. What do you need to do with that? Essentially divide by 6.022 times 10 to the 23rd to get the energy of 1. Capiche?
Okay.
So do not use per mole in this
Yeah.
equation.
You can't use that equation directly with the mole. It has to be with a photon.
So if you had 319 kilojoules per mole, you would multiply by 1 mole per 6.022 times 10 to the 23rd photons, and you would end up getting the energy per photon. And then you can use this equation. But you cannot do this directly.
Right.
Okay. So that's a fair warning, because your book does that to you. They're going to ask you, calculate the wavelength, and then you're going to find out that the wavelength is something atrocious. You're like, no way. And you're right, no way.
Yeah. So if it's like way outside the
Yeah.
spectrum.
Okay. So I don't know, maybe you guys want to call in at 1:15. I'll be doing this again at 1:15 if at your pleasure. I'm going to post this one because we did quite a few problems, and I think we talked about a number of important topics.
Yeah. What are you starting with next week?
We're going to chapter 7 next week.
Okay. All right.
This is really a short chapter when you think about it.
Yeah.
Basically, Bohr's equation, C equals lambda nu, E equals HC, E equals negative RHC over lambda, lambda equals H over MV, and then Schrodinger's equation where you have shell, subshell, and orbital. And that's basically the whole chapter. Once you start doing those equations, they become a lot simpler. And Schrodinger's, we did so much practice with Schrodinger's. I feel like you're kind of getting a much better idea what's going on there.
Yeah.
Okay.
All right. Thank you.
Good work, people. Have a good weekend. If
All
I
right.
don't see you at 1:15.
All right. Likewise. Have a good one. Bye.
All right. Bye-bye.